All right, folks, welcome back to the examples portion of the 2.5 lecture. And so here we're going to go through 4 examples, okay? 3 of these examples, examples 2, 3, and 4, should be very similar to what you see on homework number 1, whereas example number 5 is going to start to bridge into what we're going to cover on Monday and Tuesday of next week. Okay, so the focus here should really be on examples 2, 3, and 4, and example 5 is really going to lead us into the next part of our unit. All right, and so if we think about our process, okay, so our process from the first part of the video was that we had to start by determining if a differential equation was exact or not. And in order to find that, we had to identify our m, which is the coefficient function of the dx, and we had to find our n, which is the coefficient function of y. And when we take our partial derivatives now, all right, keep in mind that m is really phi sub x and n is really phi sub y. And so what we're checking is that phi sub xy is actually equal to phi of yx. And so we're going to find m and take a partial with respect to y. And when we do that, we get phi of xy, or 2x. Similarly, we're going to take the partial derivative of n with respect to x so that we get our phi sub yx, and turns out that is also 2x. And since m sub y equals n sub x, we get that this is an exact differential equation. And as such, we are able to move forward in our procedure. All right, so the second part is we are going to find phi either as the integral of m dx. So either we're going to undo this, or we're going to integrate n with respect to y. And we only need to do one of them. All right. In the video part 1, I did both types just so we could see that they both work. And in this case, I'm going to choose the second one. And I'm choosing this only because I did it before I'm making the video. So I found out that this one ended up being marginally a little bit less work. Okay. You kind of learn that through experience. But you are also welcome to do the integral of m dx. I think that one's not too bad either, and you should still get the same answer as what we get here. All right, so I did not leave myself enough room. Let's go ahead and take this and sort of squeeze it in a little bit. Take this. Oops. Take this, and let's squeeze this in a little bit. Put that up. All right, so again, I said I'm going to do phi equals the integral of n dy. And so that's going to mean that I have phi equals the integral of x squared minus 1 dy. That means that I'm integrating with respect to y. So I'm going to get x squared y minus y plus, and in the previous video, I did a c sub 1. Another way you can differentiate or tell the difference between your constants is maybe just give it a different letter like k. All right, so I'll leave that up to you. You could write a k, a c sub 1. It's really up to you. All right. Now, once we found our phi, we want to make sure. Oh gosh, I skipped a step. I'm so sorry. This is not a k yet. We are integrating with respect to y. And so that means that any function that had only x actually went away in our equation. So we should have an h of x here. That leads us to our third step, where we actually have to find h of y or h of x. And in this case, because I chose the integral of n dy, I have to find h of x. And so I'm going to find that by saying that phi sub phi sub x is going to equal the m from the very beginning. And so if I take the partial of this with respect to x, I'm going to get 2xy minus 1 plus h prime of x. Oh gosh, I am all over the place today. This is not a 1, it is a 0, folks. All right, 2xy minus 0, because the derivative of y with respect to x is 0, plus h prime of x equals, what did we have for our original m? Well, we had 2xy. So that's what I'm going to put on the right-hand side. Now, I think at this stage, we can kind of tell why I chose to do integral of n dy, and that's just because I noticed that this 2xy and this 2xy cancel out. And so I really have h prime of x equals 0. And that's a pretty easy integral to do. So when I integrate, I get h of x equals, here's where we're going to call it either c1 or k. All right. Our final step is just to take our newly found function and plug that in to what we had over here. And so maybe we can go ahead and mark off step 4 right next to this. So step 4, we're going to sub in either our h of y or our h of x, depending on what we found. In this case, it's h of x. So we'll get x squared y minus y plus k equals some constant. And we're going to go ahead and combine our constants. We actually get x squared y minus y equals c. And that, my friends, is our solution for this exact differential equation. Okay, so we kind of do like a 1, 2, 3, and then 3 really just helps us fill in something we don't know from step 2. All right. Well, let's go ahead and try example 3. I will try to make no mistakes this time so I don't confuse you over this video. All right. So we've got example 3 here. Very long and gross looking, but it's actually not as bad when we get to the integrals, okay? So let's just be patient. I think I chose this one as an exercise of how can we keep an open mind and make sure that we're not freaking out over things that look complicated and instead trusting in our own skills that we can absolutely take care of equations like this, all right? So let's start the same way. We're going to go ahead and determine, is this exact or not? And again, we're going to do that by saying that m, which is our e to the xy minus y cosine xy, we want that to be equal to phi sub x. And we also want n to equal 2x e to the 2y minus x cosine xy plus 2y. We want that to be phi sub y, all right? Now, to determine if it's exact or not, we're going to take a second derivative over here with respect to y and over here with respect to x. So we end up with m sub y or phi sub xy equals, all right, now remember, the y's are the variables, okay? The y's are the variables. So I just realized that this x is supposed to be a 2. This x is supposed to be a 2. Hope you are not judging me on the quality of today in its entirety. That's supposed to be a 2. Okay, so now let's take our derivative. I think it'll actually be a lot easier. All right, so the first term will end up with u sub, or chain rule, 2e to the 2y. And the second one, we're gonna need a product rule. So let's do the derivative of y is 1 times cosine xy plus y times the derivative of the cosine part, which is going to be negative sine xy times x, because we have to use the chain rule there as well. Go ahead and move this over. We clearly need some more room. Okay, now let's kind of rewrite that a little bit. It'll be easier to match if we rewrite it. And we get 2e to the 2x, or 2y, minus cosine xy minus plus, right? Because I have a negative xy sine xy. Whew. I hope that whatever I do when I take my partial for n with respect to x, that I'm going to get the same thing. So n sub x is going to be our phi yx. And let's zoom in over here and be very careful. Make sure Judy didn't make any typos. And we're going to take a derivative with respect to x. So we get 2e to the 2y. Those are all the constants. X is the only variable. For the second term, I'm going to need product rule again. But for the last term, that will go to 0. So I get minus, let's see, derivative of x is 1, cosine xy, plus x times the derivative of that. And then chain rule gives us an extra y on the end. And then we clean this up a bit. 2e to the 2y minus cosine xy plus xy sine xy. And check it out. Despite my many mistakes, we have fixed them all and these two are equal. So we have an exact differential equation. Okay. This is probably the beefiest part of this problem. And let's go ahead and just shrink this so we leave ourselves enough room for the rest. All right, now we're going to find phi using either the integral of m dx or phi equals the integral of n dy. All right, now in this case, I'm going to choose the first one. Okay, and again, you're welcome to try it with the second one. It should give you the same answer, but sometimes we find that some are easier to integrate than others. All right, and so let's do it. Phi equals the integral of e to the 2y minus y cosine xy dx. Now, one reason why I chose to do this version is because I noticed that this term doesn't have any x's, so that's all just going to be a constant. And this one only has one x, so that's the only thing I really need to consider as I'm integrating, okay? And so when I integrate, I obtain x e to the 2y, and then minus y over, let's see, the integral of cosine is sine of xy, but I need to do a little mini u sub where u is really xy, and so I'll end up dividing by a y here. And because I'm taking the integral with respect to x, that means that if I had any functions with respect to y, those all went to 0. Okay. So we found our phi, but now we need step 3 to help us find our h of y. All right, so we're going to use phi sub y equals n in order to find our h of y. All right, so we're going to take this expression, we're going to take the partial derivative with respect to y. Here we go. We've got 2x e to the 2y minus, let's see, if we find this partial with respect to y, then we're going to get cosine xy times x. So a little bit of chain rule plus h prime of y. And all of that is going to equal the original n in the problem. So in other words, that will equal 2x e to the 2y minus x cosine xy plus 2y. And again, it's good if a lot of things kind of cancel out at this point, like 2x e to the 2y, 2x e to the 2y, negative x cosine xy, negative x cosine xy. And so we really just have that h prime of y equals 2y, and that is a not so bad integral. We just have y squared. And again, you can put a plus k or plus c sub 1. I'll leave that up to you. And then our last step is we're going to go back to what we found, except everywhere we see the h of y, we're going to put y squared plus k. And so let me go ahead and squeeze step 4 in here. Maybe we need to shrink this just a little bit. Perfect. All right. So step 4, substitute back in, and we get x e to the 2y minus sine xy plus y squared equals c. All right. So let's get that all on one page for you in case you are wanting to pause the video. This is a good place to do that. All right. So some of these questions, as you can tell, maybe sometimes the first step is really long. Maybe sometimes that second step is long. Maybe sometimes the third one. And so this will be a really good chance for us to dive back into derivatives and integrals and partial derivatives and partial integrals. All right. Okay, let's go ahead and finish up these last two problems here. Whoop. All right, so example 4 also got some fractions and lots of terms going on. And so what we're going to do here is we're going to go ahead and see whether or not this is a exact differential equation or not. And before we do that, it might be valuable to go ahead and multiply the entire equation by dx so that we only have a dy sitting over here, okay? In fact, I'll go ahead and do that above. So we'll have 2xy over x squared plus 1 minus 2x dx minus 2 minus natural log of x squared plus 1 dy equals, and 0 times dx is still 0. I think that makes it a little easier to see that it's potentially something we have to check for exactness. All right, so here we go. We've got m, and I want to take the partial with respect to y. Okay, so I'm going to show a little bit less work here. This is my m, and I want to take a partial derivative with respect to y. The good news is there's hardly any y's in here. So the only thing we have left is just 2x over x squared plus 1. Okay. I'm also not going to rewrite my n, but rather I'm going to take n, and I'm going to take a partial derivative with respect to x. And so n, or sub x is going to be, let's see, the 2 goes away. This is a natural log situation, so it might be really nice to use a little bit of chain rule here. So the derivative of natural log is just going to be 1 over whatever that is, and then times the derivative of the inside piece, the inside piece, which is just 2x, and we can see 2x over x squared plus 1. So lucky for us, we picked a really juicy question, and it is indeed exact. Okay, so now we're going to go ahead and find our phi. Okay, so phi can equal the integral of m dx, or phi can equal the integral of n dy. And in this case, I'm going to choose the second one. Okay. So I have the phi equals the integral of my n, which is 2 minus natural log of x squared plus 1 dy. Now, why would I choose this one as my n? This was actually a pretty good example of when you should choose something over another. The reason why I chose this is because everything here is considered a constant. And so when I integrate, I just need to put a y at the end of each one. Okay. And so when I do that, I end up with I end up with 2y minus natural log of x squared plus 1y plus any function that was only with x. That had to have gone away when I integrated, when I took a derivative with respect to y. Okay. Now we'll go ahead, and find our h of x. And how do we find that h of x? Well, we're going to use phi sub x is going to equal our m. In other words, we're going to take what we have here, take a partial and set it equal to m. So what do we get? We get 2x or 2y, that goes away, minus the natural log. Well, we're going to need to take care of that. So that'll be y over x squared plus 1 times 2x plus our h prime of x, and that should equal our original expression for m, which is 2xy over x squared plus 1, 2xy over x squared plus 1. And I can tell you that I've made a sign mistake. So today is just not my day, and I apologize for that. Where is my sign mistake? Let's see if we can find it. Well, I think if we go back to the beginning part, okay, and we consider the fact that we actually have a minus sign out here, one thing that we should have done is go ahead and pull out a -1 to make this a plus sign. And so what I mean by that is we'll have our m over here minus 2x dx. But I'm going to change this to a plus because that's how we've defined the function. That's going to switch the order on the inside. Natural log of x squared plus 1 and then minus 2 dy equals 0. Okay, so maybe we highlight this in yellow this plus sign so that none of us make the same mistake that I just did here, okay? But the reason I was able to tell that I made a sign mistake is because when I got to the end, I kind of knew that things should cancel. And it turns out that things don't cancel. So it's a good clue that something went wrong earlier, okay? So now that I rearranged this order, let's see how that changes all the steps I did in between. Well, the only thing we need to change in our integral in step 2 is this should be a -2 and a plus. So we get -2y plus that natural log. And that means we have a plus over here. And now we can see that things actually cancel out. This cancels with this. And we end up with, let's see, our -2x is still there. We end up with h prime of x equals -2x. We integrate and we get -x squared plus k or plus c sub 1. Now, where did I get that 2x? Well, when I was working through the problem and discovered my mistake, I had not yet copied down all of my m. So my whole m was 2xy over x squared plus 1 minus 2x. And so that's why I needed that minus 2x over there as well, okay? Last step, we're going to go back to what we had here in step 2, except everywhere we see an h of x, we're going to put -x squared plus k. And so we'll get natural log of x squared plus 1 minus 2y minus x squared equals c. Okay. And despite my many mistakes, I will tell you that is indeed the answer to almost the answer, because I forgot that y. So y, natural log of x squared plus 1 minus 2y minus x squared is going to equal c. Okay. Now, if you had initial conditions, you would still do all of this work, and then you would have a step 5 where you plug in the initial condition, and you'll actually be able to find a numerical value for C. Okay. All right. I think I got it in me to do this last problem here. I will try not to make it too painful like example 4, all right? If you have questions on what we did in example 4 or any of the other ones, please send me a message on Discord and I'd be happy to clarify that. All right, we got one more example. And again, this example is the bridge to what we're gonna be learning on Monday, okay? So let's take a look at this and see if this is exact or not. All right, so number 1, is this exact or not? All right, so I'm going to take my m and I'm going to take a partial with respect to y. And so xy becomes x. All right, then I'm going to take my n and I'm going to take a partial with respect to x. And I get, what do I get? 4x plus 0 plus 0, so just 4x. Now, this, as it stands, is not exact because x does not equal 4x, right? We could put a little sad face here. Maybe a happy face because we would think, oh, we don't need to continue. But it turns out that what we're going to learn on Monday is that sometimes you can actually make something exact, okay? So if it's not exact, we are going to make it exact. Okay, and here's how we're going to do this. we are going to use that magical mu function from yesterday. And we're going to define mu in a very specific way. Okay, so we're going to say that mu of x equals e to the integral of m sub y minus n sub x over n dx. You could have an integrating factor with respect to y. And if you chose to do that, your mu of y would be e to the integral of n sub x minus n sub y over m dy. This kind of gives you some choice. Now, in this case, I'm going to tell you that we're going to choose the second one. And so what we're going to have is e to our, let's see, n sub x minus n sub y. That's 4x minus x. And that gives us 3x divided by m, which is xy. And I think we can tell here that the x's are going to reduce. And I have the integral e to the integral of 3 over y dy. What does that give us? That gives us e to the natural log, or 3 natural log y, or using log rules, e to the natural log y cubed, which gives us just y cubed, right? So let's take this mu, which is our multiplying factor, and we're going to multiply our entire differential equation by mu. And when we do that, we end up with, maybe let's call this a step 1.5, multiply mu of y, and we're going to get x y to the 4th dx plus 2x squared y cubed plus 3 y to the 5th minus 20y cubed dy equals 0. All right, so we've multiplied through by our mu. Let's check it again. M sub y is going to be 4xy cubed, and n sub x is going to be 4xy cubed. Now, maybe much to your dismay, because we've done so much work to only now do more work, we have an exact equation, all right? We've made it exact, and now we can finish with our steps 2, 3, and 4. All right, so we're gonna find phi, and I'm gonna choose that we do, what am I gonna choose? Well, which one of these, m or n, looks like you might want to integrate it? I hope you say this one, right? It looks shorter, everything is power rule. So let's just choose phi to be the integral of m dx. And when we do that, we end up with phi equals the integral of xy to the 4th dx. And let's go ahead and find our integral with respect to x. We're going to get x squared y to the 4th over 2 plus h of y. Okay. All right. Now we're going to go ahead and find that h of y. In order to find our h of y, we're going to say phi sub y equals n. All right. So we're going to take out what we found here. We're going to take a partial derivative with respect to y, and then we're going to set it equal to our n that we had here. And what do we get? We get 4x squared y cubed over 2 plus h prime of y equals, let's simplify that a little bit, 2x squared y cubed plus h prime of y. And this is going to equal the n in my newly exact equation, 2x cubed y, oh my goodness, 2x squared y cubed plus 3y to the 5th minus 20y cubed. All right, let's see what cancels out. Turns out these first two terms cancel out. And so we're left with h prime of y equals 3y to the 5th minus 20y cubed. All right. That's not too bad to integrate. We just got a bunch of power rule to do. So h of y equals, let's see, 3y to the 6th over 6 minus 20y to the 4th over 4, which we can definitely clean up to be y cubed to the 6th over 2 minus 5y to the 4th. And don't forget, this is when we're going to need that constant. We can call it k or c sub 1. All right, we're so close to being done. We got to do our step 4 where we're going to sub back in. So I'm going to grab what I had from step 2, which is x squared y to the 4th over 2 plus, and instead of h of y, I'm going to write what I just found. Y to the 6th over 2 minus 5y to the 4th equals c. Yeah, let's get that all on one page for you. So we've got example 5 here, which again is we're going to start to do more questions like this on Monday and Tuesday, where we think about how in the world do we handle some situations that don't fit so neatly into any given strategy. We might have to combine some of these strategies to make it work. Okay. All right, so folks, thank you so much for your patience. Let me know if you have any questions and I would be happy to help you out. All right, have a great rest of your day.